Integer pivoting. The LH algorithm follows the edges of a polyhedron, which is implemented algebraically by pivoting, as used by the simplex algorithm for solving a linear program. We described an efficient implementation that has no numerical errors by storing integers of arbitrary precision. The constraints defining the polyhedron are thereby represented as linear equations with non-negative slack variables for the polytopes P and Q in 3.6. These slack variables are non-negative vectors S in R to the N and R in R to the M, so that X in P and Y in Q if and only if B transpose times X plus S equals to 1 and R plus A times Y equals to 1. And X is greater than equals to 0, S is greater than equals to 0, R is greater than equals to 0, and Y is also greater than equals to the 0 vector. Abiding inequality corresponds to a 0 slack variable. The pair xy is completely labeled if and only if xi times yi equals to 0 for all I in N, and yj times sj equals to 0 for all j in N, which by 3.9 can be written as the orthogonality condition. X transpose times R equals to 0, and Y transpose times S equals to 0. A basic solution to 3.8 is given by n basic linearly independent columns of B transpose times X plus S equals to 1 and n basic columns of R plus AY equals to 1, where the non-basic variables that correspond to the n respectively n other non-basic columns are set to 0, so that the basic variables are uniquely determined. The basic feasible solution also fulfills 3.9 and defines a vertex X of P and Y of Q. The labels of such a vertex are given by the respective non-basic columns. Pivoting is a change of the basis where a non-basis variable enters and a basic variable enters and a basic variable leaves the set of basic variables. While preserving feasibility, 3.9, we illustrate thus for the edges of the polytope P in figure 3.2 shown as arrows, which are the edges that connect 0 to vertex C and C to D. The system B transpose times X plus S equals to 1 is here. 3x1 plus 2x2 plus 3x3 plus s4 equals to 1. And 2x1 plus 6x2 plus x3 plus s5 equals to 1. And the basic variables in 3.11 are s4 and s5, defining the basic feasible solution s4 equals to 1 and s5 equals to 1, which is simply the right-hand side of 3.11, because the basic columns form the identity matrix. Dropping label 2 means that x2 is no longer a non-basic variable, so x2 enters the basis. Increasing x2 while maintaining 3.11 changes the current basic variables as s4 equals to 1 minus 2x2, s5 equals to 1 minus 6x2, and these stay non-negative as long as x2 is less than or equals to 1 over 6. The term 1 over 6 is the minimum ratio over all rows in 3.11. With the positive coefficients of the entering variable x2 of the right-hand side divided by the coefficient. Only positive coefficients about the increase of x2, which applies to at least one row since the polyhedron P is bounded. The minimal ratio test determines uniquely S5 as the variable that leaves the basis, giving the label 5 that is picked up in that step. The respective coefficient 6 of x2 is indicated by a box in 3.11 and is called the pivot element. Its row is the pivot row and its column is the pivot column. Algebraically pivoting is done by applying row operations to 3.11 so that the new basic variable x2 has a unique column, so that the basic solution is again given by the right-hand side. Integer pivoting is a way to achieve this while keeping all coefficients of the system as integers. The basic columns then form an identity matrix multiplied by an integer. To that end, all rows which in 3.11 is only the first row except for the pivot row are multiplied with the pivot element, giving the intermediate system. 18x1 plus 12x2 plus 18x3 plus 6s4 equals to 6, and 2x1 plus 6x2 plus x3 plus s5 equals to 1. Then suitable multiples of the pivot row are subtracted from the other rows to obtain 0 entries in the pivot column, giving the new system. 14x1 plus 16x3 plus 6s4 minus 2s5 equals to 4, and 2x1 plus 6x2 plus x3 plus s5 equals to 1. In 3.13, the basic columns for the basic variables s4 and x2 form the identity matrix multiplied by 6, which is pivot element that has just been used. Clearly, all matrix entries are integers. The next step of the LH algorithm in the example is to let y5 be the entering variable in the system r plus ay equals to 1, which we do not show. There, the leaving variable is r3, giving the duplicate label 3, so that the next entering variable in 3.13 is x3. The minimum ratio test, which can be performed using only multiplications, not divisions, shows that among the non-negativity constraints, 6s4 equals to 4 minus 16x3, which is greater than equals to 0, and 6x2 equals to 1 minus x3 is greater than equals to 0. The former is tighter, so that s4 is the leading variable. The pivot element shown by a box in 3.13 is 16, with the first row as pivot row. The integer pivoting step is to multiply the other rows with the pivot element, giving 14x1 plus 16x3 plus 6s4 minus 2s5 equals to 4, and 32x1 plus 96x2 plus 16x3 plus 16s5 equals to 16. Subsequently, a suitable multiple of the pivot row is subtracted from each other row, given the new system 14x1 plus 16x3 plus 6s4 minus 2s5 equals to 4, and 18x1 plus 19.6x2 minus 6s4 plus 18s5 equals to 12, with x3 and x2 as basic variables. However, except for the pivot row, the unchanged basic variables have larger coefficients than before because they have been multiplied with the new pivot element 16. The second row in 3.15 can now be divided by the previous pivot element 6, and this division is integral for all coefficients in that row. This is the key feature of integer pivoting, explained shortly. The new system is 14x1 plus 16x3 plus 6s4 minus 2s5 equals to 4, and 3x1 plus 16x2 minus s4 plus 3s5 equals to 2. This is the final system because the duplicate label 4 given by the variable s4 that has just left is dropped in Q, where the missing label 2 is picked up. The basic solution in 3.16 is vertex D of P with x3 equals to 4 over 16, x2 equals to 2 over 16, and the labels given by the non-basic columns 1, 4, and 5. Integer pivoting, as illustrated in this example, always maintains an integer matrix or tableau of coefficients of a system of linear equations that is equivalent to the original system B transpose x plus s equals to 1 in the form C times B transpose x plus C times s equals to C times y. In 3.17, C is the inverse of the basis matrix given by the basic columns of the original system multiplied by the determinant of the basis matrix, which is 6 in 3.13 and 16 in 3.16. The matrix C is given by the integer cofactors of the basis matrix. The cofactor of a matrix entry is the determinant of the matrix when the row and a column of that element are deleted. Each entry in 3.17 has a bounded number of digits by at most a factor of n log n compared to the original matrix entries. So integer pivoting is a polynomial time algorithm. It is also superior to using fractions of integers, rational numbers, because their cancellation requires greatest common divisor computations that take the bulk of computation time. Only the final fractions defining the solution, like x3 equals to 4 over 16 and x2 equals to 2 over 16 in 3.16, may have to be cancelled.